This is Dr. Indradeep Kumar, Assistant Professor, IARE, Hyderabad. So in this video, we will see failure stresses in plate and stiffened panels. So the lecture topic will be failure stress, means the stress at which any structure will fail. Or here it what about the plate. So the stresses at which the plate fail and stiffened panel. So first, the previous section on plates and stiffened panels. So separately we had seen about the plates also. In previous video we had seen about the stiffened plate also, means the normal plate and when it's a stiffened panel or plate is there. That time panels looked at predicting buckling stress. So what happened? That time we started predicting where the buckling will be there or what will be the stress because of that buckling will start. However, as we have seen, plate retains some of their load carrying capacity even when a portion of the plate has buckled. So what happened? It's not like that this plate is there and this got buckled like this, right? So they don't have that stress. They have some stress still remains in that one, because of that it's not getting failed. Now, once the applied stress or buckled will be more than that stress, then only this plate will get failed, and that stress is called as the failure stress. So just here. Okay. So in the fact, ultimate load is not reached until the majority of the plate's stress exceed the elastic limit. So what happens? Just see ultimate load, after which the plate or any member will fail, will not reach until the majority of the plate's stress, whatever the stress is acting on the plates, either shear stress, direct stress, normal stress, whatever is there, that should cross the elastic limit. In first module, what we have seen like this. So from here, the material who obeys the Hooke's law, first it goes straight. Up to what it's straight, that is the elastic limit of that one. After some, it's a plastic. And then finally, it becomes here at the ultimate stress at this point, and after that, it's a breaking. Right. So up to this elastic limit, and elastic limit means what? After removal of the force, again it will come back to their original position. So whatever the forces is acting, once this will cross this line, right, that stresses will cross this point, then only it will come to plastic and then ultimate one. So without reaching this one, beyond that only, it can reach to the ultimate load. That's here mentioned that as what? Exceeds the elastic limit. So up to this elastic limit is means up to this, if you will apply the load and you will release, then again it will come back to original position. There is no deformation. Once cross this line, then some permanent deformation will be there in the plastic region. So means after crossing the elastic limit, only the ultimate load can be achieved or reached. Because of non-linearity caused by both large deflection and the inelastic stress. So after that, what happened? Till up to the elastic limit, it's a linear. Once it crossed the non-elastic, that elastic limit, then it becomes a plastic. So there onward, it's a non-linear. So that's why just see here, this curve type is there like this. It depends on the material, right? So now this becomes the non-linear. So inelastic stress-strain relationship. So this is only the stress versus strain relationship. Calculating the ultimate stress theoretically is difficult. So some materials are there in which case it's a finding very difficult. Then by what experimentally we are finding now, just see here like this one. Up to this it's a fine, elastic limit is there. Now after that what happens? So strain is there. So stress is increasing, strain is increasing, that is fine. So once stress will be more, strain will be more. After the elastic limit, what happened? Even if you will increase the strain but not in same proportion, strain will increase. Up to that also it's okay anyhow. So just see at this point and this point, right? Here this was strain, here is stress. Now if it will reach, then also you can see here strain is increasing, stress is increasing. But after some time what happened? This will start decreasing. So now just see here, it was here, now it's here. So though, but strain is increased, but even stress is lower than this point. That also is possible. So then theoretically how you will calculate? Because according to the Hooke's law, stress is directly proportional to strain. I simply say, right? So means whenever we will apply the stress, strain will be there. More strain will be there. But after this point, what happened here? Strain is more, but stress is less. So we cannot predict in that case theoretically by applying Hooke's law. Then what is the alternate method? Go for the experimental method. So by experimental method, they found 4 different materials. Means after up to elastic limit, we can find easily by the using Hooke's law or theoretical method. But beyond that one, it's difficult to find exactly. So what we are doing? We are finding with the experimental method. So Gerard, that is this one is a citation one. Propose a semi-empirical solution for flat plates with all 4 edges supported. So now semi-empirical, not exactly the semi-empirical half of part, means up to the elastic limit he proposed that we can get the solution theoretically, and beyond that we can find by the experimentally. So here is supported. Theory and experiment shows that after elastic buckling occurs, the average compressive stress A in the plate and the unloaded edge stress, this is sigma A average. Sigma A in the plate and the unloaded edge stress sigma E are related by the following expression. So how sigma A and sigma E is related? That is here. So sigma A average. This is bar stands for average. So sigma A average by sigma CR, where sigma CR is the critical stress, which is equals to alpha 1 into sigma E by sigma R. So just here, this is related here, sigma A average to sigma E. So in case of if it is non-linear, then here power is n. If it's a linear, then n becomes equals to 1. So for linear, it will be sigma average by sigma CR equals to alpha 1 alpha into sigma E by sigma CR. Now just see if n equals to 1 is there, then what happened? Then for n equals to 1, means for linear, for n equals to 1. So now sigma A average by sigma CR equals to alpha 1 into sigma E by sigma CR. Now this side. So sigma A average equals to alpha 1 into sigma E by sigma CR into sigma CR, because the sigma will get multiplied. Sigma CR cancel. So sigma A average will be equals to what? Alpha 1 times into sigma E. Now what is alpha 1 here? Some unidentified constant, means some constant is there of that proportion sigma average will be there. Now whatever sigma is there, of some proportion sigma A will be there. Okay. Theoretical work by Stovall and Mayers and Budiansky, right, demonstrates that. So these are who worked on this one. Demonstrated that failure occurs when the stress along the unloaded edge is approximately equals to the material's compressive yield. So now see here, according to them, failure occurs when the stress along the unloaded edge. First case, what was there? It's unloaded if all the 4 sides. Here we are seeing, right, that all 4 edges supported. Now what happened? Load applying where the load is, that is unloaded is approximately equals to the material compressive yield stress. So sigma Cy, C stands for compressive, Y stands for yield, sigma yield point. Now here we are seeing, right? So thus substitute. Okay. So now sigma CR, that sigma critical, in previous video we derived that one. That is K pi square E by 12 into 1 minus mu square into T by B square. This already we derived that sigma CR. We can use here for N. That is for this one, non-linear one. Linear one, N will be equals to 1. For that I just derive here. Thus substituting sigma Cy for sigma E in equation here. So just substitute wherever sigma is there for in terms of sigma Y. Okay, and rearranging the result, where the average compressive stress in the plate has becomes the average stress at failure. So now sigma A bar becomes sigma. So the average stress at failure sigma F bar. So sigma F bar. So now instead of sigma A bar, sigma F bar, and sigma E becomes what? Sigma C. I just substitute these two here. Yeah. So substituting for sigma CR in the above equation. So now sigma CR just substitute here, right? And then after simplifying, what we'll get? Alpha equals to this is alpha 1 pi square into 1 minus that square pi power 2 into 1 minus n by 12 into 1 minus mu square power 1 minus n. Now, so this is the sigma value, sigma CR, right? Now, just after putting here in this one, sigma CR, sigma A becomes what? Sigma A bar becomes sigma F bar and sigma A becomes sigma C bar. Just substitute here. So sigma F bar, sigma A becomes F bar, and here sig A, that alpha k power 1 minus n into T by B whole square into E by sigma C whole power 1 by 2 whole power of 2 into 1 minus n. So just substituting value here. So from these two equations, just replace sigma A bar equals to sigma F bar and sigma E equals to sigma C y. That you got here. Now just further simplify, because what we required in terms of sigma F bar by sigma Cy equals to beta into T by B. So just here beta. This is just, instead of that this insorted, they written just T by B into E by sigma Cy whole power 1 by 2, and for this 2 into 1 minus n they written as, so 2 into 1 minus n they have taken as m. So power becomes m. Here what is there? 2 is not there, right? 2 into 1 minus m. So from here 1 minus n will be equals to what? M by 2. So for this 1 minus n they have taken m by 2. So now this becomes alpha k power m by 2. So after putting here this value, so sigma C bar by sigma Cy equals to alpha k to the power 1 minus n as m by 2 into T by B, okay, by into E by sigma Cy whole power 1 by 2, right, power 1 by 2 and whole power 2 into 1 minus n. 2 into 1 minus n, what we assume that as m. So this is, so that is here. Now they assume this as beta. So beta is what? Alpha k to the power m by 2. So beta alpha into k to the power m by 2 and into this term in terms of m. So let's see where beta is alpha k power m by 2, alpha into k power m by 2, and the constant beta and m are determined by the best fit of equation to the tested at time. Is how beta will be there, because that alpha is also what? It's a constant, unidentified constant, and alpha only in terms of beta we don't. Here alpha in terms of beta, right? So once we know the alpha, according to that we can find beta. Now what is there? That this one, this power, and also we have taken according to the linear equation. So if our power was here, this n, what we assumed 2 into 1 minus n equals to m. So from here you can say 1 minus n equals to m by 2. So here n equals to 1 minus m by 2. This also we can. So here instead of this we can write 1 minus m by 2. Now failures, this one. Experiments on simply supported flat plates and square tubes of various aluminium and magnesium alloy and steel shows beta. So now here what? Beta unidentified constant, and that depends on alpha, and alpha depends on what? The type of material. So this beta also depends on the type of material, which material is there. So according to that the beta value will be there. So for that, to various aluminium and magnesium alloy and steel shows beta equals to 1.42. For this material beta is 1.42 and m as 0.85. Fit the results within plus minus 10%. Means after using that beta value as 1.42 and m value as 0.85, the value is coming nearly the either 10 plus minus percentage, means the just difference is of 10%. Sometimes it's getting 10% higher, so it is a 10% lower. So 10% is 10% just is acceptable, by because this is unidentified constant. There is no fixed value of that one. But after choosing these values for beta and m, we got just the nearer value, so it's accepted. Corresponding value of the long clamped flat. So just see now the condition also. Now in this case long clamped flat plates is there. What is beta? Beta is 1.80 and m is 0.85. So in this case again m is 0.85, but beta got changed. Now beta is here, in previous case it was 1.42, but now it is 1.80. Now again, Gerard extended the above method to the prediction of local failure. So by this method only the local failure, where it will be local failure stress for the plate elements of thin walled column. Okay, that above equation, the previous equation, this equation will be. So where A is the cross sectional area of column BG and M are the empirical constants. So just here, that is the formula here. The same formula in terms of this one, right? Here. So first, there A is the cross-sectional area of the column, BG and M are. So there B was there in previous, now it becomes BG and M are empirical constant, and G is the number of cuts required. How many cuts are there? That is G. To reduce the cross section to a series of flange section plus the number of flanges that would exist after the cuts are made. Means now any flange is there, or just see here in this image. So like angle type is there, one is connected, 2. So here G is 2. How many? What is G here? So see, G is the number of cuts required. So in this case, G. Now let's see here. In this case, if you will see, so here how many? 4 flanges are there. Okay. Now, sorry, 4, and this 4 is cut. So total G will be equals to 4 cut plus 8 flange, 12. How 8 flange? So now just see here. This is first 1 cut, 2 cut, 3 cut, 4 cut. Okay. Now just see here. 1, 2, 3, 4, 5, 6, 7, 8. So total 8 flanges are there now. Earlier it was 4, but after 4 cut, the total 4 cut plus 8 flanges. So value of G will be equals to 12. Now in this case, 1, 2, 3. So there is no cut. So that's why G is simply 3 flange and 0 cut. In this case, 1, 2, 3, 4. So again here, there is no cut. Only the flanges are there. So 4 flange. Here G, that also of 2 flange. So basic section G. So remember how to find G. First, how many flanges are there? After cutting, how many cuts are there? So here 4 cuts are there. So just cut into 4. And after that, count how many flanges are there. So total number of cuts plus total number of new flanges will give the sum of those two will give you the new value of G. Let's see here first. Here 1, 2. If this cut is not there, then it should be 3, 4, 5. But what happened? Now cut is there. Right. So how many cuts are there? 1 cut. Now how many flange? 1, 2, 3, 4, 5, 6. So now here 1 cut, 6 flange. So total G is 7. Now here again. So here 1 cut. How many? 1, 2, 3, 4. So 1 cut, 4 flange. Total 5. So this will give you the value of G. That you have to substitute here. Okay. This G value. So now same thing, sigma bar F by sigma Cy equals to beta G, where beta G in previous equation, what was that? Beta. Now this T by B depends on what? Here, that area, and G is TSK and TST. So see here. So this one, just how many flanges are there? How many cuts are there? So that TSK, TST by B, and this remains same. Only the thing, this will change, that T by B. Here directly we have taken one full this thickness, that T. Now whatever the thickness is there, if we will divide, then thickness of that T, then divided by B, that here we have taken just as the what? Area. So both equations are similar to that one. Okay. So let's see quickly once again. So failure stress means here we have to find the stress at which it becomes fail. So after the elastic limit only it can reach to the ultimate load. Means definitely whatever is there, we can say that if it's reached to ultimate load, means it's across the limit of the elasticity. Then what happened once in case of experiment, because each we cannot find by the experiment. So what we did, according to the Gerard, first up to what limit you can find by the theoretically, because when it's a linear, up to that we can find easily by theoretical method, but experimental we can find throughout. But when the linear is not there, that curve path is there, non-linear, right? That time it's a difficult to find by the theoretical method. So for that, the next is experimental method. In that only he said that the average compressive stress, that average compressive stress denoted by sigma bar A, and the plate and unloaded edge stress sigma E, where the unloaded edge is there, right? So in between that, they proposed one relation, that sigma average A by sigma CR equals to alpha 1 into sigma E by sigma CR, where sigma is stress at unloaded edge, sigma bar A is the average stress. Okay, whole power, and this is for non-linear, where if n equals to 1, then it becomes for the linear. And alpha 1 is what? An arbitrary or unidentified constant, where sigma CR is what? K pi square E by 12 into 1 minus nu square into T by B whole square. This already we derived. So just simply you can substitute here that as sigma CR. Okay. So now when sigma E, that unloaded is, becomes the compressive yield stress, means what happens? Sigma E become change to sigma CY, and sigma dash A will change to what? Sigma F bar, that is average stress at failure. So that only sigma F bar is required, that failure stress at which it will fail, that is the sigma F, and sigma F bar is just the average failure. So after substituting this value, we got this. Now just replace sigma A bar to sigma F and what? Sigma E to sigma CY. And after substituting this, after simplifying, what we will get? Alpha into K power 1 minus N into T by B into E by sigma CY whole power 1 by 2 and 2 into 1 minus N. Now let's assume 2 into 1 minus N as M. So from here, what we will get? N1 minus N as M by 2. So this becomes alpha K power M by 2 into T by B into E by sigma CY power half whole power M. So that is here. And in that they assume alpha K power M by 2 as beta. So finally, this is the formula. Just you can take this sigma CY this side. So you will get average failure. So this is the final equation. Now, that beta and M, that unidentified constant is there. So beta and M, that depends on the material that we have, because alpha depends on the material. So beta. So now beta and M we have to choose in such a way, right? So see, experiment of simply supported, okay, that should fit the result. So after seeing that one by experimental, they found for the aluminium, magnesium, alloy and steels, beta equals to 1.42 fits and M equals to 0.85. So this you have to remember. Okay, by putting these values, the answers are coming plus minus 10%. The variation of an answer is just plus minus 10% of that one. And in case of long clamped flat plates, beta is 1.8 and M is 0.8. Now same thing. Okay, so now above equation, that what we used here in another way, right? Another method of prediction for local failure stress. So this is what? Average failure stress. The sigma F bar is for average failure. Now for finding local failure stress, at what point you wanna find? For that, again he made same thing modified here, sigma CF. Now local means what? At this point, what will be the failure? Means at this point, how much stress will be there so that it will fail. Now after cutting this, suppose this is one part. Now we cut into this two part. So now one part, two part. So if you wanna find here, then at what stress it will fail. So for that only they just proposed, or they just derived from the same formula, okay, by using the previous sigma F, that failure, average failure by sigma CY equals to B into G, B G at G, just how many number of cuts are there, G into TSK into TST by A. So just simply same, this is the B by A in previous formula, this is B by A, but it depends on how many number of cuts, how many flanges are there, based on that, and remaining things same. So now according to the figure, here there is no cut, so only the flanges is there. So G equals to 2. So G is equals to total number of cut plus total number of flanges. In this case, 1 cut, 2, 3, 4 cut. So 4 cut. After that, 1, 2, 3, 4, 5, 6, 7, 8. So 8 flanges. So total G value will be 12. So for this case, G is equals to 12. So for like that, all the G value will be there according to the given section. We have to choose the value for finding the local failure stress. Okay. Okay. Thank you. So if you have any doubt, you just comment on the video, or okay, contact me so that Can I clarify your doubt? Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.